Okay, let's get started. So starting today, we're going to switch gears to some of the theoretical and algorithmic perspective in deep learning. And we're going to start off with generative models. These are mostly used for image generation and encoding images to some latent space, but not necessarily. So these are not necessarily just for images, but and it's very important that you know these mathematical tools because this is going to appear again and again. So I broke up the lecture into two parts. So here, the ultimate goal is to get familiarized with variational autoencoders, namely VAEs. And today, we're not going to go into VAEs quite yet, but instead, we're going to build the necessary mathematical tools for you to understand VAEs for the next lecture. So this is just to get you guys prepped up for VAEs. And here, I'm assuming you guys have taken a class in intro to probabilities or probability theory, or some form of that. Okay, and if you get stuck somewhere, I think you can teach yourself the necessary background. But as I said in the very first lecture, probability class is one of the prerequisites. Okay, so I took the slides from the last year, and then I pasted. To be honest, I pasted the Beamer tech files for the two lectures to ChatGPT, and tried to make it easier for students to understand. So some of the figures were drawn by ChatGPT. And there could be some rough edges. If I spot them throughout the lecture, I'll fix them. If you spot something, you can. Please, I urge you to let me know during the lecture or after the lecture. I really appreciate it. But overall, I'm really satisfied with the quality, and especially the figures look much more clean, and the organization of the lecture today and Wednesday. Okay, so the roadmap is today I'll introduce you to autoencoders, probabilistic decoder, why it's necessary, and latent variable model and ELBO, evidence lower bound. And next lecture, we're going to combine everything and formally derive variational autoencoders. So the main idea is a VAE is a special type of autoencoder whose latent space is trained to be sampleable. So deterministic version is the autoencoder. If you put a probabilistic spin on it, that's VAE. And what's nice about it is now we can sample from the latent distribution. Why is it necessary? Because after we finish training, we need to have a handle on how to sample so we can generate samples. Okay, so let's do outline. So in this lecture, in these lecture series, we're going to cover specifically on unsupervised learning. So we have already talked about supervised learning, score functions, loss functions, and etc. But we haven't quite talked about unsupervised learning. So here, the input is that you have some x. So previously, we had some x, and it's labeled y. But right now, in unsupervised learning, we don't have y anymore. We just have a bunch of x's. Okay, so there are no labels. And the goal is to learn some structured data, and it's going to be useful for a variety of ML tasks like clustering, dimensionality reduction, feature learning, and density estimation, etc. And what exactly is an autoencoder? You take in, for example, an image, and you pass it through what's called the encoder and decoder network, and it tries to reconstruct the data. So you have some input X, and encoder is typically shaped like this. So it takes in a high-dimensional object and outputs a low-dimensional feature, which is supposed to be some good feature representation of the input data. And decoder is shaped reverse. It takes a low-dimensional object in and outputs a high-dimensional raw data as output. Okay, so during training, you need both the pair of encoder and decoder. And for inference, you may, depending on your application, you may only want the encoder. So you can use it as dimensionality reduction tool. Or during inference, you may only need a decoder so that you can start from Z's and start generate data that was not included in the training set. Just to compare supervised, unsupervised, the noticeable difference from data perspective is we no longer have the label available to us. And in supervised learning, the goal was to learn the mapping from X to Y. Here in unsupervised learning, you want to learn some structure that resides in the data without having access to the labels. So why are we talking about this? I'm sure you guys went online sometime and generated images. I think typically it's going to be conditioned on your input prompt. So how do you do that? How does it work? What's under the hood, basically? So usually the objective in these domain is given your data x1 through xn, given your training data, which is sampled from data distribution. You want to learn a model distribution P theta of x, where theta is your neural net parameter that assigns high probability to realistic data. So the challenge here is we do not have explicit analytic form of P data, and thus we only have we can only sample from this distribution. And these samples are what constitutes your training data. So you have access to the data samples, but you don't know the underlying data distribution. Okay? This is not some arbitrary Gaussian with some parameter where you know the explicit form. Right? That's the setting. You only have the samples. You don't have the distribution. So the goal is to learn P theta of x, which models the data distribution. It's parameterized by theta. Okay, can you approximate the data distribution with a neural network? That's the goal. And if you approximate it well, then it would assign high probability to these real samples. Okay? So the principle of a maximum likelihood estimation is given access to n samples, data samples, you want to increase the log likelihood evaluated under your model. Okay? And obviously, you don't want to overfit to the data, right? So, for example, let's say you have in 1D, You have lots of data here, here, and here. Obviously, if you just look at the objective, the best fitting one is put a spike here. That's the perfect model, right? Right? Just looking at the objective. But that's not what we want. Let's say the actual P data looks something like this. But we ended up having these samples available. So we want to not completely zero out here in terms of probability density. So how do you balance between maximum likelihood and some form of regularizer in the probability space? That's the name of the game. So basically, we want to learn a parameterized probability distribution that best approximates the underlying true data without actually looking at the probability density function. Okay, given only the training data, how do we best mimic the underlying data distribution? So you can do it through regularization, or you can do held-out validation, right? So you fit your model based on a random subset of data. You repeat this process, and you want to pick one that has highest held-out training objective, or something like this. And as soon as we start using the neural network for P theta of x, oftentimes this integral here becomes intractable. So that's why we need to try to, as opposed to directly optimizing this, try to take an alternative approach. So one approach is to approximate this. We're going to cover it when we talk about pixel RNN, pixel CNN. Another approach is to derive a lower bound and maximize the lower bound. So what's an autoencoder? You take input X, you push it through some encoder network parameterized by phi, and it's going to output a low-dimensional feature representation Z. So Z usually has much lower dimension than input X. So it creates what's called the information bottleneck. So this bottleneck forces Z to capture the essential factors of variation of the data, so that from Z you can pass it through the decoder parameterized by theta and be able to reconstruct the original input. Right? So this is very high dimensional, and this is very low dimensional. Say, I don't know, let's call it P. So you better pack here just the essential components, and so that you can perfectly reconstruct the original input. So whatever is shared across many data perhaps could be modeled in encoder and decoder, but whatever is different about this specific data can be usually packed in this tight p-dimensional space. I usually think about this in terms of Photoshop. So have anyone used Adobe Photoshop or any image editing tool? Okay, a subset of you. So if you open up any of the photo editing or creation tool, you have these menus here. You have some tools like paintbrush or eraser or things like this. Here on the right, you have these what's called layers and logs. So this keeps the list of changes you made. So something like create a box at x, y, size height and width, something like this. And here, paint, red, the box above, or something like this. You have a text list of the changes you made. And even though your image is very high dimensional, it's basically the pixels, your changelog is very compact representation, right? You only need to store the list of changes you made, and that's enough to reconstruct this whole input. So these change lists could go into the code, and decoder is what mimics the Photoshop engine. That's how you can pack information in this tight p-dimensional space. Right, so this is high dimensional object. It's I don't know, 1,000 by 1,000 pixel object, which is very high dimensional. But here the text's very low dimensional. Okay, that's the input structure. And how do you train it? You apply a reconstruction loss. So for every training data xi, you want to first pass it through the encoder. And this is going to give you the Z. And you pass it through the decoder. It's going to give you a reconstruction x hat of I. And we're going to measure the L2 loss. This is one instantiation of a typical autoencoder. Okay, so you load an image and pass it through the encoder, decoder, measure the quality between the original data and the reconstructed version. And you want to do gradient descent on the encoder and decoder parameter. Very straightforward, right? Everything's deterministic. So what is it good for? Like I said in the beginning, you can use it for dimensionality reduction. You can just throw away everything after encoder and use the Z representation. Or you can start from this and train a supervised learning classifier theta that you can do supervised learning on. So say you have a very limited amount of training data, then it may be difficult to directly train the classifier. But once you pass it through, so stage one is learn autoencoder, ignoring Y. So, okay, so let me give you a concrete setting. So here, you have lots of data available, but only a subset of them have labels. So you have xi, yi. This is one set. Union. So you have 1 million unlabeled data, and you have, I don't know, 100 labeled data. So to rate, if you just do vanilla supervised learning, you have to you cannot use this, right? But what I'm saying is, first, just get all the X's and learn AE. So encoder learned from this have seen billions of data. So this feature representation is going to be very good. So as opposed to learning something here that has to map high dimensional X to low dimensional Y, you use AE. So AE of XI, comma YI. You learn a classifier here. Now the burden is a lot less because the classifier doesn't have to worry about mapping this high dimensional object because output of AE is very low dimensional. You can also use it for denoising. So say you learn the autoencoder and the noise, you have some images and the noise is, let's assume the noise pattern is random per each data. You have randomly added noise per data, and once you train an autoencoder, you can push noise to X and expect a cleaned out reconstruction X hat. Okay, so first train the AE on clean data, clean subset data, and during test time, if you have some noise, independent noise added per data, you can pass it through encoder decoder and expect to see a cleaned out reconstruction. So autoencoder itself can be useful for many tasks, but for the generation, it may not be so good. For generation task, so after, say you have trained an autoencoder and you get rid of the encoder, right? You get rid of the encoder here. And what's a generation task? You want to sample Z, pass it through decoder, and create some image that's generated and it's not in the training set. You want to generate a new image. So the problem is, how do you sample the Z's? You first need to sample Z and then pass it through a decoder. If you sample this from some random location that, during training, these are going to get mapped in some p-dimensional space. And we didn't force the model to put the Z's in that follow some certain distribution. We need the Z's to follow some easy to sample distribution during training so that during inference, we can sample from this easy to sample distribution and pass it as input to the decoder. So since we didn't force anything like that, these Z's are going to map pretty much everywhere randomly in this p-dimensional space. So this becomes a problem. So pictorially, it will look something like this. So let's say our P is two-dimensional. So if you look at the encoded training examples, the Z's will occupy some complicated subset of the latent space. And if you randomly sample Z from, I don't know, uniform distribution, then it may land far from your encoded training example. So there's a distribution mismatch between whatever you're using to sample Z versus where the Z variables landed in this p-dimensional space during training. So what's the end result? The decoder may produce very, very low quality outputs. So the intuition is, how do you train these models so that it follows a simple, easy to sample prior, for example, uniform or standard normal distribution, something like this. You want these Z's to follow whatever we're going to use to sample Z's during inference. Okay. That's one aspect. This is completely different thing. So remember, in today's lecture, we're not going to give you the complete picture. We're going to introduce you to various intuitions and pitfalls of AE and mathematical tools that you need to be familiar with. So mathematically, there's a connection between reconstruction loss and likelihood. So minimizing reconstruction loss with L2 loss specifically is same as maximizing the likelihood under Gaussian model. So AEs usually minimize the squared MSE reconstruction error, like this: clean input, reconstructed output. And if our decoder is probabilistic, say it outputs the mean and variance parameters given Z, so given the latent code, probability distribution on the reconstructed output follows Gaussian distribution with mean parameter and variance parameter, where mean parameter is some function which is a function of Z. So this is a neural network that takes as input Z and outputs the conditional mean of this multivariate Gaussian. So if we model this decoder probabilistically, then the log likelihood of this model is going to be, so this Gaussian, take the log, it's going to be some constant, minus 1/2 sigma squared, x minus the conditional mean. How many of you have taken engineering math 2 with me? Okay, a couple of you. So if you don't know, if you're completely lost, just Google reconstruction loss as likelihood, and something like this will appear with more derivations. So this is just Gaussian distribution. So take the log, and it's going to be constant plus this term here. And if you minimize the MSE between the clean input and reconstructed output, that's same as increasing the log likelihood of this clean data point with respect to the generated output. Okay, so the key connection is maximizing the Gaussian log likelihood is equivalent to minimizing the square reconstruction error. If you don't believe me, just write out the PDF for Gaussian and take the log, and you'll see. Okay? So that's if we have continuous data. So this, what we call decoding distribution, probability of the clean data given some latent code. If we model it as Gaussian distribution, we could even output the variance as well. But just to keep it simple, we're only going to output the conditional mean and just use diagonal covariance matrix. So Gaussian decoder implies MSE-like loss. And what if we want to model discrete data? Say we have some binarized image or something like this. How do we model our decoding distribution? In continuous case, we modeled it as Gaussian distribution, where the conditional mean is some neural network takes as input the latent code. Likewise, in binary data, we can use something like a Bernoulli distribution, a bias coin, where the bias is output from some neural network that takes as input their latent code. So, and of course, pi theta is going to output some number between 0 and 1, right? That's the Bernoulli distribution parameter, which is bias of landing in the head, right? in this case, if you take the negative log likelihood, then it's very simple. So this Bernoulli distribution, so it becomes binary cross entropy. So remember, this binary data, so this is going to be 0 or 1. And here, this continuous data. So depending on x being 0 or 1, if it's 1, then we're going to compute this portion, log of pi j. If it's 0, this is going to be vanished. It's going to be log of 1 minus 10. That's binary cross entropy loss, which we already talked about. So this is one instantiation of how you model continuous versus binary data using the same framework. So you would model the decoding distribution differently to model to reflect your characteristic of the data. You don't have to. It's just an example. Okay, so let's suppose now we want to, let's look at the inference procedure for now. So let's say we want to specifically sample from the standard normal distribution during inference. And once you sample Z from standard normal, you want to pass it through the decoder, probabilistic decoder, and it's going to output a distribution on axes using this Gaussian model. Okay? And then you're going to sample from this Gaussian here, and that's going to be a reconstruction. Let's suppose you want to follow this framework. So what is the likelihood of the data under this model? So p theta of x is, of course, you want to marginalize from the joint distribution here, right? You want to marginalize this latent variable out. That's going to be p theta of x, right? And this is just Bayes' rule. It's P of Z times a conditional distribution P of x given Z. Okay, so in English, this means this is a probability assigned to x after considering all possible latent explanations Z. Or simply just marginalization. You want to get rid of this variable that you don't want. And unfortunately, if you use neural network for this data, then this integral is analytically intractable. So that's the source of all problems. And let me lay out all the terminologies so we can speak the same language. So P of Z, this is prior over the latent variables. This is usually going to be standard normal or uniform distribution. Whatever it's easy to sample from, doesn't really matter. This is our design choice. And this is prior distribution on our latent variables Z. And P theta of x given Z, this is going to be the decoder distribution or the likelihood or generative network, mean all the same thing in the VAE context. P theta of x is our marginal likelihood, which has this nasty integral over Z. P theta of Z given x, that's the true posterior, and this is not analytically intractable as well. And Q phi of Z given x, that's going to be our variational autoencoder or variational posterior. And this is called the recognition network in the VAE context. So basically you have decoder and encoder, and this Q denotes variational distribution. So basically in high level, this guy intractable, so we're going to approximate it with Q. Q is a neural network. So by Bayes' rule, this guy in the integral, Pz given x, the true posterior, is Px given z. This guy, right? And this is same as this numerator is same as this guy, P of x given z, the decoder distribution times the prior. But the denominator is it's hard because like we said here, this analytic integration is NP hard. So by same logic, P theta of z given x is also hard. So it's intractable as well. So the true posterior, by same logic, is also intractable. So we're going to try to approximate this using neural network, which is Q distribution. We're going to put everything together in the next lecture, but today I just want to name them. Okay, so if you don't follow exactly what's going on, that's fine. Let's just at least get the terminology consistent. So for training path, we sample X. This is clean data. Push it through our encoder distribution, which we're going to call variational posterior. We're going to sample Z. This is going to output a distribution on Z. So we're going to sample from Q. And once we sample Z, we're going to pass it through our encoder distribution, the generator network. And this is going to output a distribution on X. And we're going to sample our reconstructed version from this distribution. That's how we're going to do training. For generation, though, we're going to sample specifically from predetermined prior distribution, which is easy to sample from. We're going to sample Z, pass it through our decoder distribution, and it's going to output again the distribution on the output, and we're going to sample X from here. So just by looking at this, it sounds natural that two things happen, right? One, this pair, X and X hat, should be similar. The reconstruction quality must be good. Second, this guy must follow our prior distribution. We're not gonna have this problem, right? We want to force the Z's that pass the encoder distribution to follow our sampling distribution, the prior. So two things must happen, 1 and 2, if this training is to go well. And the generation goes well. So that's the intuition, and we're not gonna just, okay, two things must happen, I'm gonna do 1 + 2 and optimize. We're gonna, in principle, we're gonna derive the VAE equation in the most principled way, so these appear naturally without resorting to intuition. But it's useful to know the intuition. Let me see how many pages I have. Wow, a lot of pages left. Okay, so, oh yeah. Okay, so to get us ready, we need these mathematical tools. So for math majors and STEM majors, I think this is elementary. But for other majors, it may be new. And we're going to cover it in details, so don't panic. So first thing is KL divergence between two probability distributions. So this is one input, second input. It's a divergence between two probability distributions. And we need to understand Jensen's inequality. And we already covered this in the engineering math class. Log of expectation of random variable is lower bounded by expectation of the log of the random variable. And item 1 and 3 is connected. So specifically, when these two input distributions are Gaussian, you can derive the closed form solution of KL divergence using the mean and variance parameters. So specifically for our VAE case, this prior is going to be fixed to standard normal in most cases. And if you have input Gaussian here, depending on whether it's multivariate or univariate, regardless, the KL distribution between two Gaussian distributions has a closed form solution. Okay, so our VAE objective looks something like this: reconstruction term minus latent regularization. This forces the posterior distribution to follow our prior distribution. If it doesn't, it's going to penalize. And we're not going to just add them together. We're going to derive it formally. Okay, so what's a KL divergence? So let's look at the simple discrete case first. So let P and Q, these two guys here, be two finite distributions on X. The full name is Kullback-Leibler divergence between distribution P and Q. And that's summation of all realizations of X, Px log ratio of P and Q, or simply expectation of the random variable X drawn from P distribution of the log ratio. So it appears from information theory, and the intuition is how much information is lost when Q is used to approximate P. And it's a divergence, not a distance, because if you flip the inputs, these are not equal in general. But intuition-wise, you can think about it as distance. If P and Q deviate from each other, you get large and large quantity. And it's lower bounded by 0, and it's not upper bounded. It can approach infinity. So if you want to minimize KL divergence, in terms of the optimization perspective, it's good because it has clear lower bound. But sometimes you want to maximize the KL divergence, but with other terms. But KL divergence is not upper bounded, so sometimes you can approach positive infinity. So it's going to be hard. For continuous distributions, I mean, it's the same thing. It's expectation of X under P distribution of the log ratio. And the important property is it's non-negative. And are we going to prove this? Yeah, we're going to prove it in the information theory lecture. So we have a lecture specifically dedicated to information theory. So you can prove it yourself. It's very easy. But otherwise, wait until the information theory lecture for more rigorous proof. So important property is it's always non-negative, and this is equal 0 almost everywhere if and only if P is equal to Q. But in general, if you swap the order, these are not going to be equal. All right? Yeah, so KL divergence is not a distance. It's not symmetric. And they mean different things. So I think we have a slide dedicated for this. If you parameterize theta to approximate P versus if you parameterize the second argument to approximate Q, they mean different things. And there's a slide dedicated in about 20 slides. Okay, and the convention in information theory is the KL divergence between two distributions is not going to be infinity only when Q gives non-zero probability, wherever P gives positive probability. Meaning the support of P must be contained within the support of Q. Otherwise, it's going to be defined as positive infinity. So it's only defined when support P is contained within Q. So for example, here, when they have no overlap, support of P is not contained within support of Q, so it's defined to be infinity. And if they have overlap, but here there's a portion of Q that sticks out, then it's still infinity. And if they have overlap and P is completely contained within the support of Q, then you have finite KL divergence. I think this is ChatGPT making mistake. For better visualization, maybe I should do something like this. Yeah, some overlap, but some portion of P sticking out. Yeah, so in plain language, Q may be broader than P, but Q cannot have holes where P has mass. Right? So where does this guy appear from VAEs? So we're going to do a full derivation in the next lecture, but it appears something like this. Your encoder distribution, or the posterior, variational posterior of KL divergence between variation posterior and prior appears as a term during derivation. So this means encoded versions of X in the latent domain. We're going to measure the KL divergence of that with respect to our sampling prior. If they deviate, we're going to get penalized. So the interpretation is KL term keeps the encoder's latent distribution close to a simple prior that we can sample from. Okay, another tool that we need is Jansen's inequality. And we covered this in engineering math lecture a lot, so I'll be brief. So a function f is convex if for all pairs of data within the domain omega, and for all real number lambda between 0 and 1, function value of the weighted combination of x and y is lower bounded by weighted combination of the function value of the pair x, y. If this is true for all pairs of point x, y, this function is defined to be convex function. If the inequality goes otherwise, it's called concave function. It's neither convex or concave. And Jansen's inequality, I think this I think better name is lemma here. Okay, whatever. If function f is convex, expectation of the function of random variable is always lower bounded by function of expectation of x. And if you don't remember this, derivation is very simple as well, and we already covered this in engineering math 2. And why don't you derive it yourself? And if you don't remember which side the inequality goes, you just draw a bowl-like function and check just draw 2 points here, and expectation of function value of x, so combination of function values here, that's going to be something like this here, and function value of expectation of x, so some expectation here, take the function value, that's another point. So this is left hand side, right hand side. So when it's bowl-like, left hand side is always greater. All right. So why are we talking about this? Log is a concave function. So for concave function g, expectation of the concave function is it lower bounds the concave function of the expectation. And for us, what this means is log of expectation is going to be lower than expectation of the log of something. And this is one of the key steps in deriving the elbow in VAE. And we'll apply it to this term here, join over the posterior distribution. Oh, okay, so there's a proof here. Okay, so KL divergence between two distributions is always non-negative and holds with equality if and only if P is equal to Q almost everywhere. And assuming common support for simplicity, meaning we already defined when it's not infinity, right? Support of Q must contain all the support of P. So let's start from definition. KL divergence is expectation of X under P distribution of the negative log ratio of Q and P. Negative log is convex function, so we're going to use Jensen's inequality here. It's going to be lower bounded by negative log of the expectation of X of the ratio. And this is going to be negative log of the Q distribution. This is going to equal 1, and log of 1 is 0. So KL divergence between two distributions is non-negative. This is going to be important as well. So just to put this into context again, so let's start with marginal likelihood. So here we need to marginalize this nuisance variable z. And we're going to insert some posterior distribution. So we're going to multiply and divide by the same distribution here. Okay, we're going to take this, multiply, divide by some distribution q. We don't know what it is yet. And we can write it as following. Expectation of z under q distribution of the ratio between the joint and posterior. And here, if we're interested in the log of the probability, then we can use the Jensen's inequality and derive lower bound. So it's going to be lower bounded by expectation of the log ratio, right? So right hand side is called elbow, and we'll do a formal derivation next lecture, but it's just giving you a preview of how all these things are connected. So elbow stands for evidence lower bound in stats community. And Yeah, Gaussian KL divergence. So if you have two Gaussian distributions, more generally in k-dimensional multivariate space, we already talked about multivariate Gaussians in engineering math 2. If this is new to you, you can do a self-study. It's not difficult. So let's say we have two distributions, P0 and P1, each parameterized by the mean vector and covariance matrices, sigma 0, sigma 1. But strictly speaking, this is not necessary because in implementation, we're going to do univariate Gaussian. So we're not going to cover, we're not going to implement multivariate Gaussian for efficiency purpose because here this is size n by n. But anyways, this is the general form. So if you have two multivariate Gaussian distributions, if you compute the KL divergence, you have closed form solution. Trace this term inside the Gaussian and log determinant ratio minus the dimension. This is the general form. So this becomes standard normal. This becomes univariate Gaussian. You can simplify from here. And in VAEs, we usually only need special case against standard normal distribution. Because we want to make our lives easier and make this guy easy to sample. So how does it simplify? If the distribution to the left here, this is the variational posterior, and let's say this is univariate Gaussian. So this is the conditional mean, taking x outputs the conditional mean on Z, and we have diagonal covariance matrix, which may or may not be the output of the network. In most implementations, this is going to be just simple sigma squared, constant. And the right-hand side is going to be, like I said, standard normal. So KL divergence between one univariate distribution and standard normal simplifies as following. This is the mean variance -1 minus log of sigma squared. And we don't need to rely on sampling to compute the KL divergence because these are two Gaussian distributions. And you can derive it yourself. Maybe it's fun to derive it for univariate case. Just use definition of KL divergence and insert Gaussian PDF, and you can do it. Or if you feel like challenge, then start from multivariate Gaussian case, derive this equation, and then insert the definitions here into this form. You should arrive at the same answer. And when we actually implement this in code, encoder usually outputs the mean and log of sigma squared for numerical stability, as opposed to directly outputting the sigma squared. Okay, so let's see. So this is the KL term between the posterior and the prior distribution, right? We derived it here. So let's take a moment to analyze what's happening. So if the posterior outputs a distribution that exactly matches the prior distribution, which means mean of 0 and variance of 1, then what do we get? So theoretically, KL divergence outputs 0 when two inputs are identical. So let's check. Okay, so mean is 0, variance 1, -1, log of 1. Then we get 0. Okay, so it checks out. If the encoder outputs distribution that's identical to standard normal, then we get 0. And if the encoder outputs a conditional mean that's very large in absolute sense, then what happens? This increases quadratically, and we get penalized. So from this KL regularizer, we're going to receive a large penalty if the encoder distribution outputs something that has large mean. And if it outputs a very small or very large variance, it also increases the KL divergence. So we have two competing terms here, sigma squared and negative log of sigma squared. So if this is very large, we get penalized. And here, if this is very small, we have log of very small number and minus sign, so we get a large penalty as well. Okay? So the KL term pushes the variational posterior towards standard normal distribution. Okay? If the mean deviates, get penalized. If the bell curve shrinks too much, get penalized. It becomes too broad, you get penalized. Okay, so let's do a preview of the VAE. Let me see how many slides. Okay. So this is just a preview and not giving you full derivation yet. So it looks something like this. Given some training data, has two parameters for encoder and decoder. And this is the full objective. This lower bound, you sample X from your database, push it through encoder. It's going to give you distribution on the latent code. You sample your code Z. So this is step 1, sample X. Step 2, pass it to the encoder. Step 3, sample Z from the encoder. Oops. Step 4, pass it through the decoder and evaluate log of the probability of the real data X under the decoding distribution. So decoder must put lots of probability mass density for this sample X. So otherwise, so in other words, this is going to be reducing the MSE loss for Gaussian models, minus the KL divergence regularizer. So it's a combination of the reconstruction quality and latent variable regularization. So first term encourages good reconstruction. Second term keeps the latent codes to be close to our easy to sample prior. So we're going to derive this in the next lecture, train it and generate samples. So, what's this elbow? So elbow, if I write it with equality, looks something like this. So log likelihood of the data under our model is the elbow plus KL divergence between the variational posterior and remember we named it true posterior, which is intractable. So anyone remember the slide number for our variable list? We had a table 19. Okay, thanks. So PZ is prior, P of X given Z is decoder, P theta of Z given X is a true prior, a true posterior and intractable. And Q was our neural network to approximate P. Okay, all right. And as we know, KL divergence between two distributions, if the supports satisfy our assumption, which is the case if they are both Gaussian. So this is going to be non-negative. So since KL divergence is non-negative, the log likelihood is lower bounded by our elbow. Elbow is our VAE objective. So the gap between the elbow and log likelihood is the posterior approximation gap, this guy. This is the KL divergence between the posterior, variational posterior, and true posterior. And how the training goes is we want to increase elbow, increase the lower bound on the log likelihood, reevaluate elbow after we have updated the parameters with gradient descent, and then increase elbow again, reevaluate the elbow on the data, and repeat. So as opposed to increasing the log likelihood directly, since it's intractable, we're going to keep evaluating its elbow and try to increase the elbow. In effect, as we increase this elbow term, it tries to reduce this posterior approximation gap, which is the KL divergence between the variation posterior and true posterior. Okay, so let's try to summarize what we need to remember for today's lecture. So we talked about vanilla deterministic autoencoder. It takes X, the data, maps it to low dimensional Z, reconstructs the data from Z. VAE takes a probabilistic spin and makes the latent code probabilistic. So the encoder distribution, we model it as Gaussian or Bernoulli distribution with conditional mean and variance generated by the encoder network. So encoder doesn't directly create Z. Instead, it creates the parameters for the Gaussian distribution for Z. Okay? It defines the distribution on Z, which then we're going to sample from. And prior is simple and sampleable distribution, anything you like, but in most cases, standard normal or uniform distribution. And the objective in VAE is to increase the reconstruction quality and also decrease the KL divergence between the posterior distribution and the prior. So summary, the generative models, all generative models, the goal is to do this. You want to learn the data distribution, which is inaccessible. You only have access to the samples from P of X. So you want to approximate P of X with P theta of X. And once you learn this, you can sample from this learned neural distribution. And autoencoders are useful for learning latent representations, but for a generation task, we cannot use it directly because it's going to leave some holes in the latent space, and it's going to be different from our sampling distribution. And reconstruction loss can be interpreted as negative log likelihood, and KL divergence measures mismatch between distributions, and talked about Jensen's inequality, KL divergence between two Gaussians have closed form. And next lecture, we're going to derive the elbow without resorting to intuition. We're going to just derive it mathematically, and it's going to get connected to intuitions again. And in the remaining couple of minutes, just wanted to mention, so in our lecture, so when I introduced KL divergence, I briefly said there are two modes. One is you want to approximate the true distribution with, okay, so the setting is you want to approximate true distribution P with respect to a neural network Q theta. And what happens if you put it to the right-hand side versus left-hand side? If you put it to the right-hand side and try to minimize KL between P and Q theta, what happens is it's mean seeking or mask covering. And if you put it to the left-hand side to minimize KL between Q and P, it becomes mode seeking. It locks into one of the modes here. Why? It's going to be a homework. And it's going to be theoretical homework and also exercise where you guys implement the mode seeking and mean seeking behavior. Also, what we didn't like about KL divergence is it's not a distance metric. It's not symmetric. And in terms of optimization perspective, more important thing is it's not upper bounded. So if you optimize with KL and want to increase it, then a lot of times you're going to see positive infinity and it's going to be a pain in the ass. So alternative is to use Jansen-Shannon divergence. So if you have distribution P and Q, swap the order with the mean distribution. So measure KL between P and M, KL between Q and M, where M is just average of P and Q. This is symmetric, obviously. And square root of Jansen-Shannon divergence is a metric. You can prove it yourself. And if you use log base 2, it's upper bounded by 1. And if you use natural log, it's upper bounded by log of 2. This is going to be important for a GAN lecture. Okay? So you can measure whether the optimization was successful or not because you already know the upper bounds. And you can characterize what happens at optimality, which is very important for optimization. So even though you may not achieve optimum, at least you know what's going to happen in optimality. That's very important. So last slide is F divergence. So there we talked about KL divergence, JSD. There is a broader umbrella, which is called F divergence. So for a convex function F, with a bias set to, if you insert 1, it has to output 0. This is easy. You can just subtract it from the function. The F divergence is defined by expectation of the random variable x under Q distribution of the function of the ratio P and Q. So KL divergence is a special case where F is T log T. Jansen-Shannon divergence is also a F divergence. You guys figure out what the function F is. And it's not needed for VAE, but more general, this is also connected to GANs and more generic family of generative models. So useful to know. All right, that's it for today's lecture. Thanks.